All right, we're going to have a little lesson right now on theorems about roots of polynomial equations. So right up until now, we've been working with polynomial functions and polynomial equations. What's the real difference between a polynomial function and a polynomial equation is that a function is referring in the form of f of x, and you might have something like x cubed plus 3x squared plus 7. We're talking about the function, we're talking about the graphs, the inputs, the outputs, but a polynomial equation might be you solving when does x cubed equal negative 3x squared, oh boy, running out of room here, minus 7, and while you solve that polynomial equation, you're going to bring everything over to one side and get it equal to 0 and solve from there. So you need to watch your directions and know, are we talking about a function right now? We're going to find the x-intercepts of this function, the max and min, the y-intercepts. Are we going to figure out when it's increasing and decreasing? When is it hit a maximum or a minimum? Or are we solving an equation? In an equation, you're essentially really finding when this polynomial function and this polynomial function intersect each other. When you're solving an equation, you also might be accounting for imaginary or complex solutions, whereas if you're dealing with a function, you might not really care so much about the complex solutions because it's not going to affect our graph. They're not really going to be in an application, so you have to consider what the directions are asking you to do. All right. Now, you might have caught on a little bit and kind of noticed that our polynomial equations or our polynomial functions, the number of solutions is really normally matching the degree of our largest exponent. Sometimes it is less than the degree of our largest exponent, but that's if you only accounted for multiple solutions once. So if you list every single solution, say you got a solution of 2, but you got the solution of 2 3 times, well, 2, 2, 2, you keep going from there, your degree will equal the total number of solutions. Now here I'm using the word solutions. So you're going to have the words zeros, you're going to have the word roots, you're going to have the word solutions, you're going to have the word, the phrase x-intercepts, answers, points of intersection, yada yada. You're going to be doing the same idea every single time. So let's get into this a little bit more. So let's go look at this. Let f of x equal a polynomial function. Any input value which results in an output of 0 is a 0. Okay, that's where the name comes from. It's a nickname of 0. It's like a last name. All of them, when you plot them on your x-axis, it's like 3, 0, negative 2, 0, square root of 5, 0. They all have a y value of 0. Your input is always the x value, and your output is always f of x or y. So those are all going to end up equaling 0 in order for it to not move off of your x-axis. 0 implies 0 movement above or below, up or down, off of your x-axis. So I went over 3, up nothing. I went left 2, up or down nothing. Square root of 5, up or down nothing. Now, another thing, square root of 5 is what kind of a number? Do you remember? Square root of 5 is irrational. You cannot write it as a ratio of two integers, so it's an irrational number. If f of x, my polynomial function, had all integer coefficients, and square root of 5 is a solution or an x-intercept or a root, which we'll delve into more in a little bit, that means that negative square root of 5 will also be a solution or a root or a 0. All right, these irrational solutions, when you have a polynomial with integer coefficients, which is typically going to be the case when you're in algebra 2, when you have that, your irrational solutions will come in pairs. So I like to think irrational starts with the letter I, and we have two eyes on our face. Our eyes on our face, they come in pairs. So you have to remember that your irrational answers are going to come in pairs. All right? Anyway, continuing a little bit more. When solving a polynomial equation, now I'm using the word equation, the solutions or roots are zeros. But to elaborate a little bit more, we typically solve for all roots, and that's not all the time, but a lot of times you have to read your directions. You have to be a critical reader. We solve for all roots And if we're solving for all roots, that will include your complex roots, a plus bi, or if you want to refer to them as your imaginary roots, if you like to remember that better. But complex is of the form a plus bi, a real and an imaginary part, roots as well. Now, here's the other catch. Similar to over here, how we said our irrational roots come in pairs. Well, guess who else comes in pairs? Our imaginaries. So if you got a root, say you got it from quadratic formula, you got 2 plus 3 square root 7, oops, duh, it's supposed to be imaginary, 3i square root 7 over 5 as a root or a solution. Well, guess what else you got? You definitely also got 2 minus 3i square root 7 all over 5. So our imaginary roots, and imaginary also starts with an I, also come in pairs. So this would be that value and that value. Now you don't write them as comma 0, comma 0. These don't land on the x-axis, right? They're imaginary roots. We can plot these as numbers in the complex number plane, but they are not going to be x-intercepts. We do not write them as a y value of 0 as an ordered pair. So they are part of our roots or our solutions when you're solving an equation, but they're not going to have any impact on our x-intercepts when we're solving for strictly x-intercepts. So I need you guys to keep all that in mind. So we account for all imaginary, irrational, and real roots when we're solving a polynomial equation. So again, putting a little bit of a note here, when we're solving for roots, okay, we're going to have our rational roots, rational. We're going to have irrational, and we're going to have complex, which for a nickname, because it starts with an I, it might help you remember, we're going to have our imaginary. Okay, so our roots can be rational, irrational, and complex, also known as, for right now, imaginary, okay? Now, moving on, we're going to kind of come up with a little bit of a rule here. Let f of x be a polynomial with integer coefficients. That's what I mentioned before, integers. You got to know what an integer is. Well, the symbol for an integer, I'm just going to write it up here somewhere, is going to look like this little fancy z up there. And our integer in set notation, we could write dot, 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 say -2, comma, -1, comma, 0, comma, 1, comma, 2, dot, dot, dot. And that should sort of explain what an integer is. It can only be written as a rational number if it were over 1. It's a whole number, but whole numbers start at 0 and they only go toward infinity. They do not include negatives, so it's a positive or negative or a 0. Whole number, the natural numbers, if you remember, they start at 1. Whole numbers start at 2. Integers include the negatives and they include 0. Okay, so let f of x be a polynomial with integer coefficients, so our numbers in front of our x to the first, or x to the second, x to the third. Therefore, 3 dots in a triangle means therefore. Therefore, our function f of x can equal, now this might look scary to some of you, this is just notation showing a polynomial in standard form. A sub n is going to represent a coefficient times x to the n. N is indicating it's the coefficient of the term that has the nth power. N could be 10, n could be 2, n could be 1. Plus a sub 1 less than that, x 1 power, 1 degree less, right? So if that's 4th power, then that's 3rd power. Then that would be the 2nd power. Dot, dot, dot over here just implies we could have a whole bunch of terms. Maybe we don't have a lot. Here, 1st degree, coefficient of that term. And then a sub 0 is just really our constant. Next to it is an invisible x to the 0 because we should know x to the 0 is equal to 1. We talked about that already. And we went over y. So this is our polynomial. Our polynomial with integer coefficients. Now, elaborating, when f of x, this polynomial, equals 0, if you set it equal to 0 and we want to solve, got a couple things that have to happen. Our integer roots, our solutions, but our integer roots must be factors of a sub 0, and our rational roots must have a reduced form of p over q where, and we're going to talk about p over q, but let's rewind for a second. Integer roots must be factors of a sub 0. Now let's think about this. When we were in earlier sections in this chapter, we wrote polynomials from the zeros or from the graph. If you already knew the solution, if you already knew the x-intercepts, and we were saying that those were our only solutions, well, what do? We're like, oh, x equals 2, x equals -3, and x equals 1 are solutions to my third degree polynomial equation. What is that polynomial? Well, if x equals 2, the way we solve is we use zero product property. So we had to get it equal to 0. So I'm going to subtract 2 from both sides. Now I have x minus 2 equals 0. I'm going to add 3. Add 3. Well, I have x plus 3 equals 0 now. I'm going to subtract 1. Subtract 1. I have x minus 1 equals 0. So I'm kind of working backwards now. These were the factors that I had set equal to 0, which means that they were factors of my polynomial, x minus 2, x plus 3, x minus 1. So that's factored form, or 0 form. If I needed standard form, you would expand everything. When you expand everything, that constant term at the end, will equal the product of these numbers over here. That's a quick little shortcut, right? So -2 times 3 is -6 times -1 plus 6 is going to be the constant at the end of my equation. And then my first times my first times my first, when I'm over here with my largest degree, x to the 1, x to the 1, x to the 1, well, x to the third. In this case, it's 1x to the third. That's going to be my leading term. Leading term. So what this one rule over here says, integer roots must be factors of a sub 0. Anytime I have an integer root, like 2 or -3 or 1, it's going to be a factor of that number right there. So that should make sense. But then we might have rational roots at times. Well, where can rational roots come from? All right. If I had expanded this whole thing and came up with this big, beautiful polynomial equation equal to 0, couldn't I have multiplied the whole entire equation by 5 or divided everything by 5? Or couldn't this even be 5x minus 2 before anything? If this solution were, say, 5 halves instead of, not 5 halves, it would be, I'm sorry, 2/5 instead of 2, I could have had a 5x minus 2. Well, if this leading coefficient right here, our leading term, was 5x, then that would make our actual leading term of our polynomial 5x cubed. That's going to have an impact on everything. We're going to get into that more later, but that's where rational roots come into play. Ratio, proportions, must have reduced form of p over q where? Now, what is p and what is q? We're going to define p and q right now. P will be a factor of a sub 0. And not just a factor, but an integer factor. And then Q is, I'll write it better this way, an integer factor of a sub n, or the leading term. And like I said, I'm going to get into that a little bit more later, but we'll get there in a second. Here's our next example, or next piece of notes here. So we last concluded, when solving a polynomial equation, any rational roots are of the form p over q, where p is a factor of the constant term and q is a factor of the leading term. All right, so we have to have it in standard form in order to look at it this way. You're going to see why this is helpful in just a few minutes. Again, we mentioned irrational and imaginary roots may exist. The number of unique or distinct roots will be less than or equal to the degree of the polynomial. So let's dive into this and have something to talk about here. Example 1, find all roots of, all roots. You have to be a good critical reader. If it said find the x-intercepts, then you can't have imaginary or complex solutions. You throw those out. But it says find all roots. So we want all of the answers. And we just said that the number of roots will be less than or equal to the degree of the polynomial. So I could have up to 3 roots when all is said and done. We also mentioned that irrational and imaginary roots come in pairs. So I either will have 3 real roots, or I will have 1 real and 2 irrational, or well, really irrational is real, I'm sorry. 1 real and 2 imaginaries, okay? Or I could have 1 rational and 2 irrational. I can't have 3 irrational, I can't have 3 imaginary because I have integer coefficients. So I want the roots of this polynomial equation equal to 0, and then I'm going to classify each root as being rational, irrational, or imaginary, aka complex. Okay? Now, normally, if I were going to try to solve 2x cubed minus x squared plus 2x plus 5 equal to 0. If I were going to try to solve this, what we've been doing up until now is we have been factoring right away. If you want to go and try to factor, normally the first way we try to factor is we look for a greatest common factor. Well, I definitely don't have a greatest common factor in this example. Then we might try to factor by grouping. I can't factor by grouping. I see that right away because this proportion is 2 to 1 and that's 2 to 5. I'm telling you, not going to work. We can't factor by grouping. So you can't just factor this by quickly looking at it. So that's why we need another method. We need another way to go about getting this factored. So if I wanted to try to divide this, because when we try to see if we have a factor of a number, we divide and we see if we get a remainder of 0. I have so many things that I could try to divide into this. The list goes on and on forever. Numbers are infinite. But not when you have a rational root theorem that tells you any rational roots are going to be of this form. Well, now I'm going to have a finite list. So what are the factors of my constant term? I need to make my P over Q here. My constant term is 5, so I could have positive or negative 1. I could have positive or negative 5 over, what are my factors of my leading term? My leading term is 2, so I could have, again, positive or negative 1 and positive or negative 2. Now let's kind of clean that up a little. 1 over 1, positive or negative 1, 5 over 1, positive or negative 5. Now put each of them over the 2. 1 over 2, positive or negative 1/2. 5 over 2, positive or negative 5/2. So that gives me, instead of an infinite number of possibilities, I now have this finite list. I have 8 suspects, 8 numbers that might work when I'm trying to find rational roots of this polynomial equation. Now, how do I decide where to start? Really, it's up to you. If you love fractions and you really want to go nuts and try the fractions first, sure, go ahead. But we also learned remainder theorem in an earlier section, where if we plug these numbers in, just like the rules for what a 0 is that we mentioned just before, if we plug this number in as an input and get 0 as an output, well, it's a 0. And a 0 and a root qualifies the same thing. And our roots come from, or zeros come from our factored form. So if I plug in 1, what do I get? I get 2 minus 1 is 1. 1 plus 2 is 3. And 3 plus 5 is 8. So 1's not going to work. If I try negative 1, negative to an odd power is negative. So I'll get negative 2 minus 1 is negative 3. Minus 2 is negative 5 plus 5 is 0. So negative 1 works. All right, well, one of my roots is x equals negative 1. That's one of my roots. I'm going to use that to help me get 2 more roots. Again, they could be imaginary, irrational, or they could be rational. We're going to find out. I'm going to divide. Technically, you're dividing by x plus 1. X plus 1 is a factor when negative 1 is a root. These are equivalent statements, so I'm going to divide by that. Okay, so we have negative 1 as a root. We know it's a root because we plugged it in, and we use basically zero product property, and it follows the definition of a 0, that if we plug that number in as an input, we get an output of 0. We tested it. That means it's a 0. Zeros are a subset of all the roots. So it's a root. If it's a root, that means x plus 1 was the factor. To find the other factors, it would be in our best interest to divide by x plus 1. Now you could do long division, but since it qualifies as a linear factor with a leading coefficient of 1, then we can do synthetic. The number that goes in this little corner, in this little box, is going to be the same as the number that is the root or the x-intercept, but the factor is the only one that has the opposite sign in there, okay? So there's -1. Here I have third, second, first, and no power, no placeholders needed. So 2, -1, 2, and 5, leaving some room to do my synthetic. And what do we get here? We bring down the 2, 2, bottom times box, -2, -3, we add them straight down. Bottom times box is 3, add them straight down is 5. Bottom times box is -5, 0. Other rule of thumb, box, comma, box is an ordered pair on your graph. So box number over here, box number over here. So 1, 0 is a point on the graph of the function y equals, in this case, 2x cubed minus x squared, squashed over there, sorry, minus x squared plus 2x plus 5. So if we got a remainder of 8, at least we have the point -1, 8. It's a point on the graph, so sometimes that comes in handy. So don't completely throw it away, erase it, and scribble it out. Now, that is a factor. We wrote it over here, so I'm going to rewrite it, x plus 1. We divided a cubic by a linear. That gives us a quadratic. These numbers imply that 2x squared minus 3x plus 5 is the other factor. This is this factored. Now I know this looks factorable, but I promise that if you try, it won't factor. We're still solving though. So we know this is going to give us that one answer of -1. I know I keep rewriting it back and forth, but if I have to solve this, what do? We use quadratic formula, all right? X equals -b plus minus the square root of b squared minus 4a times c is 10 all over 2 times a, which is 4. X equals, see I have two answers here, the one with the plus and the one with the minus. 4 times 10 is 40, 9 minus 40 is -31. Square root of -1 is I. So that means you have 3 plus minus I square root 31 over 4. This is 2 complex roots right here. And then this one is 1 real rational root. Altogether, we have 3 roots, okay? We're going to look at the next example. What are the rational roots of this polynomial right here? Now here, you notice I did not write the same directions that I wrote on the last one. Oh, we did classify already. On this one, I said find all roots. That means irrational, that means imaginary or complex, it means rational. Here I said what are the rational roots. So I don't care about the irrational or complex / imaginary. Now, when you're equal to 0, you're solving an equation. We're going to use our rational root theorem to make our list of factors, okay? So we're going to make our list of the possible factors. In the directions, sometimes they'll say list all possible roots, rather. List all possible rational roots. If they want you to just list, that's all you have to do. But don't try to use that as an excuse to not do every single example. Be like, oh, I just thought I was supposed to list the possible ones. No, read the directions, follow the instructions. If we're going to start off by listing, though, my list of possible rational roots is all the factors of this, which is the p right there, plus or minus 1 and plus or minus 2, over all the factors of this, 1, 3, 5, and 15. Now, if I write that a little bit better, that gives me 1, 2, 1/3, 2 2/3. These are all positive and negative. What else do we have? Sorry. 1/5, 2/5, and last, plus and minus 1/15, plus and minus 2/15. So again, instead of having infinite possibilities, I have a finite list. How many are on my list? 1, 2, 3, 4, 5, 6, 7, 8, 16. I have 16 numbers on my list. I want to try to see what would work. I could start with 1. 15 minus 32 is negative 17. Plus 3 and plus 2, that's not going to give me 0. Negative 1. Negative 15 and negative 3 will give me negative 18. And a negative 32 plus 2, that's not going to give me 0 either. Plugging in 2. Plugging in 2 is kind of annoying. I'd rather just do synthetic. 2 cubed times 15, no thanks. So I'm going to put 2 over here. I'm just going to go right into synthetic now. Plug in 2, I get 15, negative 32, 3, 2. Bring down the 15, bottom times box, add them straight down. Negative 1, negative 2, there we go. So that works. So 2, 0 is on my graph. That means x minus 2. So this is on f of x if I were to graph it. This is a factor, and x equals 2 is a root. This is all the stuff we can gather from that alone. So over here I'm going to write x minus 2, and I'm going to write 15 x squared minus 2x minus 1, still solving, equals 0. Now maybe this factors, maybe it doesn't. I'm just going to try a little in my head to see if it factors. If you can't do it in your head, then do grouping or AC method on paper somewhere, or use quadratic formula. You got to figure that out. I can get a negative 5 and a positive 3, and that'll give me a negative 2. Negative 1, 15x squared is good. So what are my answers? X is 2. X is negative 1/5. X is 1/3. I have 3 solutions or roots. You could also write it out like this. You could write it in set notation, so fancy little bracket. We could list them. So maybe I'll go from least to greatest. Negative 1/5, 1/3, and 2. So I could write my answer like that, whatever way we want to look at it. Now, this list of possible factors, if you look, or possible roots, sorry, rational roots. These numbers are all on that list. Earlier, one of the rules we were looking at said that if you're going to have a rational or an integer root, over here, if we're going to have an integer root, okay, over here, sorry, we said that integer roots must be factors of that last term, and we talked about why. If I look at this example, I have this term where that's not equal to 1. If I wanted this to equal 1, that's when factoring even quadratics was easiest, when that equaled 1. Because it's an equation, I could really divide everything by 15. Well, that would be x cubed, and then that would be 32 over 15 x squared. That would be 3 over 15, or 1/5 x, and then that would be 2 over 15. So these are all the things that I can multiply to get 2 over 15, right? 2 times 1 over 15, 1 times 2 over 15, 1/3 times 2/5, and 2/3 times 1/5. These all multiply as pairs to get 2/15. So that's another place where that list really comes from. If we make that a 1, that's our Q area. If that's a 1, or we want to make it a 1, we divide by 15, and now we'll have P over Q instead of just P. Okay? So these are my roots, and this one is all finished. All right? So that's the end of this for now, and we'll have another little video in a little bit that has to do with having irrational roots and imaginary roots, as well as writing the polynomials from those irrational or imaginary roots.